Hello. So for this video, you're going to get something that you don't see often from me, which is I'm actually going to read to slides. Probably my least favorite way of presenting something, but this section on estimation is very graphical and much better to use the slides than my own drawings, so to speak. And so what we're going to do is look at estimation. Now, estimation is a technique, I would say, in where I have my degree in physics, we use estimation a lot to get ballpark answers or to get an idea of where the answer may be. And it's a very useful technique to mentally calculate things and to also get an idea of the tools you're going to need to use by estimating. And so one of the best ways to estimate is to round. And rounding is a technique of getting close to a number. And if we look at our rules here, we want to look to the right of where the rounding is to occur. And if it's 5 or greater, we round up, where we add 1 to the digit to be rounded and replace everything else with zeros. If the digit to the right is less than 5, we don't change the digit and we replace everything with zeros. And then we'll use this approximately equals to let us know what our rounding is going to be like. So let me come over here and let's get this back here. We'll come back here. And so we're going to look at 35,782.14. And this is a number we can round. So let's first round it to the nearest ones place. Now what I tend to do is I tend to put a line over what I'm going to round. And our rule says look to the right. And this is less than 5. So I replace everything to the right of this with zeros. Now if we have zeros after the decimal place, we tend not to write the zeros. And we would say this. And so I would write this as approximately equal to 35,782 because I rounded to the nearest ones place. Now I can take 48,921 and we're going to round it to the nearest 10,000s. So I put a line over the place I'm rounding and I look to the right. Now this is greater than 5, so I add 1 to this and I replace everything to the right with zeros. And the nice thing about rounding and what we're saying is we're saying that if I measure in 10,000ths, this is closer to this than it is to 40,000. And that gives us a good basis to estimate from. I can add, subtract, multiply with 50,000 instead of 48,921, and I'll be close to what the answer would be with the real number. And here's an example of the world population, and they round it to the nearest 100 million. So the digit that we're looking at is 100 million is the 4. We look to the right, it's a 7. So we increase this to 5. And we replace everything else with zeros. And we get 7.5 billion instead of 7,476,242,056. And I'm going to jump through the different rounding places. Now, when we round to a decimal, the same thing happens. But instead of putting zeros to the right, we truncate the decimal, because decimals, we don't need those extra zeros. The distance from the place value, from the decimal point, holds the place value. So in this case, we're rounding to pi, and we're going to do it to the nearest hundredth. So we come over to the hundredth place, and we look to the right, and it's 1, so we don't change this, and we drop off everything else. Now, what helps with rounding is when I have a series of numbers, I can round them. And that helps me do a calculation rather quickly. In fact, this is a really good example. Is when you're out shopping, I walk through the grocery store, and as I'm picking things up, I round them to the nearest, usually quarter, because I can add quarters in my head. But here they're rounding to the nearest dollar. And so sometimes you round up, sometimes you round down, but the two should cancel each other out, and you should get close to your total amount. And so here's all the purchases. Right, $2.59 for detergent, $5.17 or for bread, $5.17 for detergent. And so as we round to the nearest dollar, we get numbers that are easy to add versus trying to add these in our head. And so 3, 5, 4, and 9, 8, 12, 21, and we get a total. If we compare it to the actual cost of $24.17, of $20.67, which is what happens when you add these whole things here. Apologize, the problem in the book was going, hey, you were mischarged something. I will say one of the things I tend to do is when I get things, when I'm doing this, I would always round this up so that I never undercount. But that's because I want to make sure I have enough money when I go to the register. But so estimation is a tool to make calculations easy for us. And in the case of rounding, we put it to numbers that we could calculate in our head so that we're in the roundabout area. Or in this case, we thought we were overcharged. We can quickly add up in our head and go, that's about $3 more. All right. Another thing we're going to look at are pie charts or circle graphs, which give us the ability to round in their own right. And so here we're going to look at a pie graph. And what happens is the entirety of the graph is a whole, and each chunk talks about a particular percentage. And so we visually get an idea of what the bigger areas are. Looking at this, I can see this darker blue. The decline in physical abilities is 41%, with the decline in mental functioning being 32%. In fact, the definition of old age seems to be decline versus ideas of reaching a specific age, retirement, becoming a grandparent. A decline in ability seems to be how people define old age. And we can see this visually because it takes up more space. So it gives us a way of estimating what we're dealing with. And so circle graphs are a good way of giving us an estimate. So let's just run through, And so using a census, there are Americans 25, if we use that circle graph, we can figure out the number who define old age by a decline in physical ability. So if we have 219 million, and we can round this number. So I would round this to 200 million. So let me come over here, get this. Oops, wrong. Sorry about the mouse noises. So we're going to round the population to 200 million. And what we're going to use is we want to know the decline in physical ability, which is 41%. So if I come back here, 41% is 41 per every 100 million. So I have 2 of those. So that's 81 million people in that age group would think that decline in physical ability is part of old age, right? Because 41% is 41 for every 100, and I've got 200 million or 81 million. And so this is how estimation helps us. Helps us focus on the smaller parts of the numbers that we can use to generate a result. It always sounds odd just hearing this click, 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 click as I work my way back through different parts. All right, and so that's how estimation helps us. Let's look at a bar graph. Whoops, hit one wrong. Bar graphs use horizontal bars to represent each item, and so the height of a bar graph helps us make predictions. And again, predictions is the key to mathematics. We want to predict what's happening. We want future references. So in this bar graph, we have the birth year of males in red and females in yellow in the U.S. Notice females slightly have a larger life expectancy than men. And there's many mechanisms within society that make this happen. A lot have to do with risk factors and a larger physicality in work, which ages someone a little more quickly. And so even though the life expectancy has been going up, it is going for both genders. There's still a prevalence for a longer life for women. And so we can look at a man's increased life expectancy around to the nearest hundredth of a year for each subsequent year. And so we can do the idea of that we're looking for the pattern in between these. So if we come back and look at this, if we look at total life expectancy, 77.1 at the end of the graph, and the life expectancy at the beginning of the graph, we can take the difference over the number of years. So I'm going to spell out what the slide's doing here. Hold on. So the life expectancy for men at the end is 77.1 years. And they started at 65.6. And so if we subtract these, right, we get 11.5 year difference in life expectancy. And then in the number of years, that was from 2020 to 1950, or 70 years. And so we can turn this into a division. And this is the point where I normally run to the calculator. Long divisions, a skill that we should have, but it's okay to use a calculator. To work on these, let's see here, 11.5 divided by 70 is about, I get 0.16. And there's more decimal places here, but I'll round it to the nearest hundredth. And what we've done is, this is the expected life expectancy increasing per year. And notice how my language, I'm using per to talk about the division. And so this is life expectancy increase per year. And we've created a rate. And let me go back to the chart here. Which is the calculation we get. And so we could say that in 2021, that for men this would go up 0.16, or it'd be 77.2.3 if we round. And for each subsequent year we could add towards this. Now that's assuming that life expectancy always increases, and one of the things that we've seen recently is that life expectancy is decreasing due to some social economic changes. But that's what data and mathematical predictions let us do. All right, another form of graph are line graphs. And line graphs match a value at a given point and then link them together. Now the purpose of a line graph is to show little slopes, or how things are changing from year to year. And so a line graph shows a percentage, in this case of college students who smoke cigarettes, which has been decreasing. And so if we want an estimate of how many smoked in 2010, we go to 2010. So let's see, we have to look at this axis, which there's 90, 94, 98, 2002, 6. So 2010 is here. We come over here, and we see that we're in between 16 and 20, about halfway. So we'd say 18%. And that's how we use a line graph to make estimations. All right, so this is how estimation can help us predict things from the different data types we have.